Okay, hello everybody. So here we are identifying the characteristics of arrow pushing patterns. So the very first pattern that we're going to be looking at is a nucleophilic attack. And initially when we first look at this, we want to understand what we're seeing. We see a bromine atom with a negative formal charge, and we see a compound with a carbocation, which is that positive formal charge is an indicator of. So we see that this is actually 1, 2, 3, so it's a tertiary carbocation. And we also see the double arrows, which means that this is a reversible reaction, which means it's constantly going back and forth until it reaches equilibrium. So what we want to look at is the red arrow. Where is it indicating? It is indicating that this electron pair from the bromine atom is attracted to that carbocation, which makes sense because it wants to stabilize the carbocation since it has a hole in its electron density. And once that reaction occurs, we see that it creates both a stable bromine and stabilizes the carbocation. The next reaction that we want to look at is the loss of a leading group. So this is very similar. This is basically what we're looking at is the reverse reaction of the above reaction. And what we want to see is exactly what is happening with that arrow. What is it indicating? So we identified that it's pointing to the bromine atom, that bond. So that compound now, that carbon atom loses the bromine atom, which causes it to return to being a carbocation. And again, it's going to have a positive charge, and the bromine atom is going to have a negative charge. The next reaction that we want to look at is the proton transfer pattern. So again, first thing that you want to identify is kind of just what's going on. You see that there's two arrows. What are they pointing at? Where are they pointing to? And what is the result? This is a reversible reaction, obviously. So this is just one part of the reaction as a whole. This is one pattern that we want to identify. So the first, we see one arrow pointing from the H2O, and the H2O we already know is stabilized, but there's an arrow that is pointing towards the hydrogen atom, which is bonded to a positively charged oxygen atom. And we already know that oxygen atom, like it's not stable when it's positively charged. So it has a hole in the electron density that needs to be filled. And that is what that arrow right next to the oxygen is indicating, that this sigma bond, once the hydrogen is lost, once the hydrogen actually is transferred to the oxygen, the H2O, then this electron pair returns to the oxygen. And what we see is that it stabilizes our oxygen atom and the formal charge is gone. This H2O actually turns into H3O+. The next pattern that we're going to look at is C+ rearrangement. So the first thing that I see here is the positive charge on the carbon. And we already know that, carbocations not very stable. However, this one is a secondary. We want to identify what it is first. This is a secondary carbon because it's bonded with two other carbon groups. And the carbon that is on its left is actually very stable. However, what we see is this red arrow is indicating a rearrangement of that methyl group to the unstable carbocation. And this is a forward it's an irreversible reaction. And we see that the previous secondary carbocation becomes a tertiary carbon, but it is much more stable than what it was previously. And even though our previously stable carbon atom becomes a carbocation, we see that there's two tertiary carbocations, which means that as a whole, this compound is a lot more stable than it previously was. And finally, we see that all of these sequences and patterns being utilized in one sequence of reactions. The first one that we identify is a proton transfer. So we see a very similar reaction where there is an oxygen atom that a hydrogen atom is transferred to an oxygen atom. Now this does create a formal charge as we see here, However, the next reaction causes it to be a little bit more stable, and we lose that H2O group completely, which stabilizes it. But of course, we're left with a carbocation. And once again, the reaction is moving forward so that way it can stabilize the carbocation. So this one right here is a secondary carbocation, and we see a rearrangement of a methyl group. And once that rearrangement occurs, that carbocation becomes a tertiary stable or more stable carbon atom, and it causes the other carbon to become a tertiary, slightly less stable carbon, a carbocation, because it is actually, it has the formal charge. But this becomes actually stabilized with that same bromine atom that we actually saw in the beginning of the reaction. And in the end, our final product is in fact a stable compound. So we just want to continue to review these sequences and identifying these patterns with obviously different compounds and molecules and reactions, but here you go.